Hey, good evening everybody, boys, girls. Working on a little bit of calculus today. As you can see, we will specifically be trying to find higher order derivatives of functions. Now, you probably know what a good old derivative is at this point, and really, in order to view this lesson, you should know a lot of the basic differentiation rules. You should know how to use the power rule, you should know how to differentiate e to the x, ln x, several different types of functions. You should also know how to use the chain rules, the product rules, quotient rules, all of those. All right, now I'm going to specify what the lesson goal is here, and this will clarify what I mean by higher order derivatives. When we're finding higher order derivatives, what we're really learning to do is to find successive derivatives of a function, okay? And so I need to give you an example of that. Let me proceed and do that. What is a higher order derivative? Well, here we're given a function, a basic power function, and when we differentiate this, of course, the power rule is what we're going to use. But where you're used to being asked to find out what f prime of x is, or in other words, you're used to being asked to find the first derivative of x, what it's asking you to do here is to find f prime of x. All right? Now, what that notation is trying to indicate to you is that you're supposed to find the third derivative of that function, f of x. And when I say the third derivative of a function, what it means is that we're going to differentiate that function, f of x, and we're going to find f prime of x. All right? And then, once we find out what f prime of x is equal to, then we're going to take its derivative. We're going to take the derivative of a derivative. And that'll help us to find out what I would call f double prime of x is. And then once we are able to find out what the derivative of the first derivative is, now we're going to find that we would have what's called the second derivative. And then that second derivative, or f double prime of x, we would differentiate it in order to find the third derivative, f triple prime of x. Does that make some sense? Let's try it out. All right, so as I explained, we need to find out what the derivative of that function f of x is to start. We're going to find out its first derivative, and we're going to use the power rule, so we'll multiply the exponent of each term by the coefficient, negative 7 times 3, 21. We'll decrease the exponent by 1. All right, got that. The derivative of the first term, you see, negative 21x to the 6th, plus 12x squared. And then you should know that the derivative of a constant term is 0. So actually then this is the complete first derivative. All right. Now all we're going to do is we're going to keep taking successive derivatives until we have found f triple prime, or the third derivative of x. Or rather of f of x, excuse me. And as this is a very simple rule that we're following, I'll just go ahead and kind of write down what the next two derivatives would be. Hopefully it's fairly clear to you. The second derivative, f double prime of x, would be negative 126x to the 5th plus 24x squared. And then that makes the third derivative, f triple prime of x, equal to negative 630x to the 4th plus 48x. Make sense? All right, now I want to help you make a couple of observations, and I want to ask an extension question for this particular function that we were differentiating. First of all, I need you to make the observation that this was a power function, and so what I'm going to ask you to do in this extension is going to be something that applies to power functions specifically. And a little bit beyond that, actually, because there's a lot of things that are power functions. I'm referring to what happens whenever you differentiate a power function and all the exponents of your terms in your polynomial are just whole numbers. The simple observation to make is that every time you differentiate such a polynomial, the degree of the polynomial simply is going to decrease by 1 for each successive derivative, right? So our first derivative was a 6th degree polynomial, then the second derivative was a 5th degree, third derivative is a 4th degree polynomial. All right, so based off of that, I need to teach you a little notation here. So I'll do that after I ask the question that I wanted to ask here. We ought to be able to find out what, say, the 21st derivative of that function f of x is. Now, the notation I was wanting to teach you here is that it gets a little cumbersome to keep adding apostrophes for every derivative that you want to find, and you really can go on almost an unlimited number of iterations for most differentiable functions. You start just writing the number of the derivative that you're trying to find in parentheses, just like this. So if I was wanting to find the fourth derivative, I would write just f and then the 4 in parentheses, and that would indicate that I was looking for the fourth derivative of the function. All right, now back to that 21st derivative that I was just asking you to find. Well, if what's happening with this polynomial as we differentiate is that the degree is decreasing by 1 every time, eventually, isn't that exponent going to become 0? And so you're going to be differentiating a constant, and the derivative of a constant, as we had said up here, is just 0. And so that derivative is going to have to end up being equal to 0 if you differentiate enough times. Okay? Now that's not going to be true for all functions. It's not even going to be true for the majority of functions, but it is true when you're differentiating these power functions, or really probably better said, the polynomial functions that have whole number exponents. All right, let's try another example. You can see here that I'm asking us to find the fifth derivative of a function. Now, why do we have to differentiate 4 times? Well, we actually don't have to, because I didn't tell you what f of x was. What I've told you is that the third derivative of some function f of x is equal to 2 square root of x. Now, an interesting question that you'll address at a later time, if you've not studied integral calculus yet, is if this is the third derivative of the function, what was the original function f of x? All right, kind of fun to figure that kind of thing out, but that's not what we're doing here. What we're doing here is we're saying we know the third derivative of a function. What's the fifth derivative of the function going to be? And hopefully, fairly obviously, we're going to differentiate this twice to get to here, right? Because the derivative of f triple prime will be the fourth derivative of f, and then the derivative of that will be the fifth derivative of f. All right, now part of why I chose this example is I wanted to remind you, you need to rewrite functions in a smart way before you differentiate. And so we're going to rewrite this in power function form. Let's do that. So of course then f triple prime of x, which you could have written if you preferred as the third derivative of x, like that. There's actually other notation that you could use as well that I'll explain momentarily. And that, in this case, was equal to 2x to the 1/2 power, right? And so, let's find out what the fourth derivative is. All right, so we'll do a half of 2, so that's just 1x, and then decrease the exponent by 1, x to the negative 1/2 power, which you could write as 1 over the square root of x if you preferred. Actually, this is a neater way of writing the final answer if the fourth derivative was the final answer. But both are acceptable in most cases as far as IB is concerned, and that's what I'm trying to teach here. Well, let's go on and find out what the fifth derivative of x is. And one thing I do want to point out to you is that even though this is a neater looking way of writing the fourth derivative, it's not the best way to write if I'm going to then differentiate it, because if we're trying to differentiate this thing, we want it written as a power function, and so we might as well have just left it in that x to the nth power form that we had before, right? So I'm going to use this function the way I wrote it before I cleaned it up in order to do this differentiation. Alright, so negative 1/2 times 1 would get negative 1/2 x, and then subtract 1 from the exponent, so that would give us negative 3/2 power, which this is our final answer, so I don't mind making this look a little bit neater than it is right here. And it could then look like this. we could say that's negative a half times 1 over the square root of x cubed, which is then negative 1 over 2 square root of x cubed. And I'd be pretty happy with that answer. Many of you will understand how you might go ahead and write that as negative 2x square root of x if you just simplify the radical that's down there. Anyway, that part, it's great if you get it. Don't need to. The goal here was to try to learn how to find successive derivatives. So that's what we've done. We went from the third derivative to the fifth derivative. Now, if you feel you've got down the concept of what we're trying to accomplish here, feel free to stop the video and ignore this next example. So this next example is going to be a bit of a fun one. Challenge, I've labeled it as, and I just wanted to show you one of the cool things that you can do when you're working with higher order derivatives. There are some circumstances where the answer works out in kind of a fun way, and this is one of those as far as I'm concerned. Why this will be more difficult is the fact that we are going to have to use the product rule with this, and so if you don't want to bother listening to this part of the video, all right, fine. But if you're up for a challenge, maybe you even try to do this for yourself before you listen to me so you could pause the video and try. But I'd love for you to listen as well. So let's get down to business here. We're trying to find the 10th derivative of that function f. Now, it's rare that you're ever going to be asked to actually differentiate a function, maybe even like 3 or 4 times, much less 9 times, which is what we're asked to do here. So if you're ever asked to find a very high numbered derivative of a function, what is implied is that there's probably some kind of pattern that you can utilize, and that's going to be the case here. And the way we're going to find the pattern is we're just going to get through the first derivative or 2 derivatives or 3 derivatives or whatever for the function that's given. All right, let's do that. Well, so here we go. Let's go ahead and find out what f prime of x is. And I am going to have to use the product rule as I am differentiating a multiplication problem, right? I've got the multiplication problem sine of x times the cosine of x. And I imagine that you know that the way you differentiate such a product is there's many ways of remembering this, but what I always teach is go ahead and multiply the first function as it is by the derivative of the second function, and then multiply the second function times the derivative of the first function and add those products together. All right? So the first function times the derivative of the second function. Well, that would mean I'm just going to multiply sine of x by the derivative of cosine of x, which I will trust that you've learned at this point is sine of x. All right? And then I'm going to go ahead and take the cosine of x, that second function, the second factor of my product, and I'm going to multiply it by the derivative of the first function, and the derivative of sine of x is cosine of x. Now, small mistake, good for you if you caught it. In that first bit of that derivative, I said the derivative of cosine x is sine x, when in fact it's negative sine x. All right, there we go. We can continue. Let's make that look a little bit neater. Often when you're finding successive derivatives, you do want to clean things up before you continue. And this would be negative sine squared of x plus cosine squared of x. All right, well, now we're on to find the second derivative. Told you we're going to be looking for a pattern here. You can't find a pattern after 1 iteration, can you? But hopefully after 2, we will be able to start to see a pattern forming here. All right, now I do want to point out that we have a chain rule that we're going to have to apply to differentiate this. Perhaps it'd be easier, in fact, to think of that function as the opposite of the sine of x squared plus the cosine of x squared, so that you can see that we've got trig functions inside of power functions here. Now, I'm assuming you know the chain rule here. Here's how we'll do that differentiation. For each of these terms that are functions inside of functions, we're going to multiply the derivative of the outer function by the derivative of the inner function. All right? That's a simplistic way of saying it. And my outer function being a squaring function, I'm going to go ahead and multiply. I'm going to bring that 2 to the front, multiply it with that negative sign. That would give me negative 2 times the sine of x. And then the inner function for that term was sine of x. So I've got to multiply this result, the derivative of the outer function, by the derivative of the inner function, which would be a cosine of x, right? Okay, and then for the second term, we've got again an x squared function for our outer function, so that would give us 2 times cosine x. And then we've got to multiply that by the derivative of the inner function, and the derivative of cosine x, as we said a bit ago, is negative sine x. And then let's start using some observational powers if we can here. Negative 2 sine x cosine x and 2 cosine x times negative sine x, well, those are like terms, aren't they? They're really both equivalent to this negative 2x, or sine x cosine x bit right there. And so if we've got negative 2 of something, and then negative 2 more of it, we've got negative 4, in this case, sine x cosine x. And so what you're going to be able to see then is that the second derivative of the function was simply negative 4 times the original function, sine x cosine x right there, right? Now, does that pattern hold? Well, let's take a couple more derivatives and see. And I'm going to shorten kind of the way I'm differentiating here because we can be a little more clever about this. The way you find the derivative of this term, we could just say is that you're going to find out what negative 4 times the derivative of sine x cosine x would be. And we've already figured out what the derivative of sine x cosine x would be. That's this negative sine squared x plus cosine squared x bit right here. So we should have negative 4 times negative sine squared x plus cosine squared x. All right, and then the fourth derivative of our function should be negative 4 times the derivative of this little bit right here. So negative 4 times the derivative with respect to x of negative sine squared x plus cosine squared x, which we've already determined that the derivative of that expression, yeah, right there, was negative 4 sine x cosine x, right? And so that means we're going to get negative 4 times that value right there. Or in other words, we're going to get 16 times sine x cosine x. And so at this point, we can verify that we have found a pattern, can't we? Because after we differentiated the original function twice, we ended up with something that was just negative 4 times the original function. And then when we differentiated that twice, we've ended up something that's just negative 4 times what it was, right? So every 2 derivatives, we're just multiplying the original function by negative 4. And so to get to that 10th derivative that we were looking for, we can just go ahead and multiply this result by negative 4 a couple times, 3 times in fact, and we'll get there. So the 6th derivative of f with respect to x is going to be negative 64 sine x cosine x. And then the 8th derivative with respect to x of that function f would just be 256 sine x cosine x. And then go ahead and multiply that by negative 4, and you've got your 10th derivative of our function, or a negative 1024 sine x cosine x. Now for you real sharp ones out there, I could go ahead and ask you to find out what the nth derivative, well, what the 2nth derivative, that'd probably be the better way of going, of x would be, and you could figure it out. I won't explain, I'll go ahead and write out the answer, but as the clever ones of you would be able to figure this out. It would have been negative 1 to the nth power times 2 to the 2nth power, and then times sine x cosine x. And really what I'm trying to show you here that's pretty cool with these higher order derivatives is a lot of time with higher order derivatives you end up with some pretty cool sequences that arise, and so you tie in another area of mathematics altogether there, right? Great. I much appreciate your attention here. Hope you've learned something fun and that you can apply it for yourself in your math class. Thanks a bunch. I'll catch you next time.